We are now on the last of our annotated introductory PowerPoints, and we are now about to cover the most important topic in all of Bio 201, the most important topic in all of Bio 202, and the most important topic in all of healthcare and the practice of medicine. That topic is homeostasis. I think a lot of students in Bio 201 don't get how important this is. In Bio 201, remember we cover 4 organ systems. Do you remember which one? That's a little quiz for you. Do you remember? Integumentary, skeletal, muscular, nervous. Remember, those are kind of like, the underlying, the streets, the sidewalks, the telephone lines, the railroad tracks. In Bio 202, when we get into the internal organs, there is not a single class in Bio 202 where I don't talk about homeostasis at least 10 times during the class. Homeostasis is, ultimately, the practice of medicine. When someone is sick, they are basically out of homeostasis. And what medicine tries to do is get them back into homeostasis. It's a lot more important than you think. It's a big deal. So learn it well. You're going to have a homework assignment on this, and you're going to have a quiz on it. And on your first exam, I will test you on it again. That's how big of a deal it is. So believe me, it's a big deal. Start learning it right now. Greek words homeos, same, and stasis, state. In other words, your body is always trying to stay in the same state. You try to keep your temperature about the same. You try to keep your blood sugar about the same, and so on. Your body is always trying to do that. Homeostasis refers to the body's ability to maintain certain physiological parameters within a relatively narrow range. Think about that. Say that again. Refers to the body's ability to maintain certain physiological parameters, values, within a relatively narrow range. If you go too high or too low, you are out of that range and you are out of homeostasis. What are some examples? Blood glucose should be between 70 and 100 milligrams per deciliter. Throughout the semester, I'll always try to let you know when numbers are important, and you do have to know them, and when they're not important and you don't have to know them. These numbers are important. You must know them every day for the rest of your life, starting right now. Your blood sugar should be between 70 and 100. Standard measurement for many blood values is milligrams per deciliter. That's 1/10 of a gram. one 1,000th of a gram for 1/10 of a liter. It's just a standard value. Get used to it. The metric system used throughout science and medicine. I think United States and Suriname or something are the only 2 countries on the planet that don't use the metric system. In any case, or maybe it's Myanmar. I don't remember. Doesn't matter. Blood pH maintained between 7.35 and 7.45. You must know that number. Remember, pH is a measure of your acid-base balance. What's neutral pH? 7. That's water. What's below 7? Acid. What's above 7? Base. So notice your blood is slightly basic. In physiology, we don't usually use the word basic because you don't know if when someone says basic, they mean like acid base or whether they mean basic like simple. So we say alkaline. So your blood is normally slightly alkaline, 7.35 to 7.45. Your body temperature should be right around 37 degrees Celsius. Did you say 98.6? Fahrenheit's for sissies. Celsius is what we should be using. Although several of my former students who work in a hospital say that their hospital uses Fahrenheit. I don't care. It's just humans. Do whatever you want. Homeostasis constantly being disrupted. So external stimuli, heat, cold, lack of oxygen. Think about it. When you go outside and it's really hot, like it is right now in May, June, it'll get even hotter. That's really hot. What does your body do to try to keep you from overheating? Yeah, you sweat. Your body is trying to return you to homeostasis. See? What happens if you go outside in the winter and it's really cold? If your body gets too cold, you'll die. You'll die of hypothermia. What does your body do to try to raise your body temperature? You shiver. See, your body's trying to get you back to homeostasis. See what a big deal this is? See how it comes up over and over again. Internal stimuli, so digestion. When you eat a big meal, suddenly you've got tons of glucose in your blood. Well, that's not good, so you secrete some insulin to get the glucose out of your blood. When you exercise, your body temperature goes up. You got to cool it back down. Psychological stress. That can raise blood pressure and so on. That's why people talk about, coping with stress. It's more important than you think. Stress is a killer. And pregnancy. Oh my God, you've got this little parasite growing inside of you, stealing your nutrients. Yeah, that's going to put you out of homeostasis. Disruptions are usually mild and temporary, like going outside in the heat and so on. Large or long-term disruptions to homeostasis can result in death. In other words, for example, in a graveyard, what the tombstones really should say is, born 1973, permanently out of homeostasis 2017. Okay, that would be another word for death. Permanently out of homeostasis. That's what it is. Notice here a fish swimming around in a lake or a stream. The oxygen is not equally distributed throughout the water. So see on the top graph, in the shallow regions there's less oxygen. Out in the middle where it's deeper there's more. Well, the fish is swimming from one part of the lake to another. The fish has various internal mechanisms to smooth out the oxygenation. The fish has to have oxygen all the time. So it has various mechanisms to maintain homeostasis even when the external environment is not really conducive. So homeostasis, we have how many organ systems again? Remind yourself, 11. Of the 11 organ systems, there are 2 that control the other 9. Those are the endocrine system and the nervous system. They can work independently, or usually they work together. The endocrine system uses chemical messengers in the blood called hormones, whereas, the hormones bring about relatively slow but long-lasting changes. So when a hormone is released into your bloodstream, it travels through your body, it binds to receptors on your organs, goes down and causes changes in the very metabolism of your cell. Think about bodybuilders, the ones who cheat using anabolic steroids. Do they take a shot of anabolic steroids and they wake up the next morning and they're all pumped up? No, it doesn't work like that. The steroids will take weeks to get you all beefed up, okay? So slow but long lasting. What happens when a bodybuilder stops using steroids? Do they wake up the next day and they're like back to normal? No, it takes a while for those changes to go away. So the endocrine system, very powerful, long-lasting changes, but relatively slow to take effect. Nervous system, just the opposite. Nerve impulses are electrochemical, so chemicals called neurotransmitters and ions produce electrical currents, electrochemical. Nerve impulses bring about relatively fast but short-lived changes. So when you are going to scratch your head and you reach up to scratch your head, think about that. Your hand moved very quickly and it's scratched, and then it's done. So nerve impulses come about very quickly by comparison, and they're very short-lived. You scratch for a couple seconds, then you're done scratching, all right? Short-lived changes. Homeostasis is regulated by feedback systems, so your body is constantly monitoring what's going on, and feedback systems let your body know what's happening so that your body can then make the changes you need to. So, for example, on the right, you're driving 80 miles per hour. You go miles per hour. And suddenly you go, whoops, I'm going too fast. I want to get a ticket. Of course, unless you're in Phoenix. If you're driving 80 in Phoenix, people will be passing you. But so you slow down. Well, if you slow down too far, now you're going 20. It's like, damn, semi's beeping at you. Better speed up. In other words, you need to try to keep your speed, assuming on a normal highway, freeway, 60, 70, somewhere in there, right? You can't go 100, you can't go 30. That's kind of what's going on here. And when you do go too fast or too slow, a feedback mechanism is what's going to either slow you down or speed you up to get back into the proper range. So homeostasis, feedback systems consist of these principal components. There is a stimulus, either external or internal. So an external stimulus might be it's hot, it's cold, all right? Some painful thing is stabbing into you. Could be internal. Your blood glucose is too high. You've got a pain somewhere in your abdomen. That's a stimulus. That's going to cause a change that's detected by a receptor. You have lots of receptors in your body. Your body doesn't know what's going on unless there are receptors for it. So you have receptors for pain. You have receptors for temperature. A very important part of your brain, the hypothalamus, has receptors for lots of things. Blood glucose, osmotic pressure, and so on. You have to have a receptor in order to know what's going on. The receptor is going to monitor changes and send signals to a control center. Now the signal is going to be sent pretty much always using either a hormone or a nerve impulse. Control center would be like what I just mentioned, the hypothalamus in the brain. It monitors your body. The hypothalamus is like a control room at like some big power plant or whatever. You've got a whole wall full of dials and gauges and meters and so on. That's the control center. It monitors everything. So once again, you have a stimulus. It could be from outside or inside the body. You detect something, the stimulus, with the receptor. The receptor then sends a signal using a hormone or a nerve impulse to the control center. So if things are okay, if the temperature is fine, then the control center says it's fine. Everything is copacetic. We don't need to do anything. But if it's too hot or too cold, the control center has to take action to try to fix the problem. So the control center uses effectors. And once again, the control center will communicate with the effector using a hormone or a motor neuron. So for example, if it's too cold outside and you start shivering, the effectors would be your muscles. If it's too hot and you start sweating, the effectors would be your sweat glands, right? So see, effectors are what actually bring about the change. The control center knows that something needs to be changed, but the control center, like the hypothalamus in your brain, it can't go anywhere. It can't travel. So it sends out signals to other parts of your body and tells them, fix it, okay? Those are the effectors. As a result of the effector doing something, you will have a response or a result, all right? And then what you need to do is the hypothalamus will monitor it again. The control center will monitor it and make sure that it's okay. If it's not, then you keep going through this loop over and over again, okay? Homeostasis, ultimately the main theme throughout the course. So that diagram at the bottom is a good one. The stimulus impacts a receptor. In this case, it's a neuron that goes to CNS, means central nervous system. That doesn't have to be the control center. Control center could be an organ, could be your kidney, all right? And then again, the control center has to tell the effector what to do. It'll do that using a hormone or a nerve impulse. And then there'll be a response or a result. For me, either word is okay. Let's use an example here. Ooh, ladies, we got a guy out there fishing on the ice. He looks kind of lumberjacky and hunky. And ice fishing. Any of you going ice fishing? I don't get it. Most people I know who go ice fishing is just an excuse to go out and get drunk on top of a frozen lake. They hardly ever catch fish. But so the stimulus here would be cold body temperature. You have temperature receptors in your skin. They'll send a signal to the hypothalamus. Hypothalamus will say, damn, it's cold out there. And what it will do is it'll cause the blood vessels in your skin to constrict, to pull blood away from the outside of your body into your core. That conserves heat. And then it'll tell your skeletal muscles to start contracting rapidly, shivering we call it. That's going to generate heat, because remember, muscles, you make ATP. When you make ATP, you generate heat. And that will bring your body temperature back to normal. So there you go. That is a feedback loop. Okay? See how easy? See how cool that is? And now, ooh, here's a real lumberjack, ladies. Or guys. Anybody can like lumberjacks. It's fine. Let's say it's really hot outside. Skin sensors, temperature sensors detect that heat. Hypothalamus says, damn, it's hot out there. So the blood vessels in the skin will now dilate, bring blood up to the surface of the body, let the air try to cool it down, and it'll cause the sweat glands to start producing sweat, and then by evaporative transpiration, you will cool down. So there you go. See, there's all the elements: the stimulus, the receptor, the control center, the effector, and the response or the result, okay? Now then, there are two different flavors of feedback loops. Let's talk about negative feedback loops first, okay? So a negative feedback loop, a response reverses the original stimulus. That's a negative feedback loop. Now I know you're familiar with the words negative and positive, meaning bad and good. Get rid of that right now. Don't do that. Negative feedback loops are good. Negative doesn't mean bad. Negative means that it reverses the original stimulus. So for example, if it was hot, if your body is overheating, and your body then does something to cool down, that will be a negative feedback loop, because you reverse the original stimulus. You were getting too hot, the feedback loop caused you to cool down. That's a negative feedback loop. It's good, it's not bad. If a response enhances the original stimulus, then it's a positive feedback loop. Yeah, a little coronavirus there. In this case, you might wonder, wait, what? When would you know, oh my God. Positive feedback with temperature would mean that if you're outside and you were overheating, your body would cause you to overheat even more. You're thinking, that's crazy. That would never happen. We'll see that, in fact, negative feedback loops are much, much more common in the human body. But there are positive feedback loops. We'll look at those in just a moment. So negative feedback loops, again, much more common. Control of blood pressure would be a good example. All right, if your blood pressure increases, that would be the stimulus. Pressure receptors in the walls of your arteries will detect that. They'll signal the brain. The brain's the control center. Brain gets the input, signals the heart to slow down, tells the arterioles, small arteries, to dilate. Those are the effectors. And what's the response or the result? Your blood pressure returns to normal. There's a classic negative feedback loop. All right. Here you see on the left, there you go. You're too cold, you shiver and you vasoconstrict. That brings temperature up. If you're too hot, you sweat and you vasodilate. That brings the temperature down, right? So there you go. And on the right, you can see buildings work basically the same way. You got the thermostat. If it gets too cold, the heater comes on. If it gets too hot, the air conditioner comes on. You got your HVAC, HVAC, all right? So that's it. Now, a positive feedback loop, again, what would an example of that be? That's weird. Well, childbirth. There's an example of a positive feedback loop. Let's work this through. So, contractions of labor push the baby's head into the cervix, which is the neck of the uterus, and that causes the cervix to stretch. And that's the stimulus. Stretching of the cervix because the baby's head is starting to poke through. There are stretch receptors there. Those are the receptors. They sense the stretch and they send signals to the brain, which is the control center. The brain releases a hormone called oxytocin. Remember, the nervous and endocrine systems are usually the control systems. And that will cause the uterus to contract even harder. So notice, the uterus was contracting. Now what we're going to do is we're not going to cause the uterus to relax. We're going to make it contract even harder. Why are we going to do that? Because we're in the process of giving birth. So what happens is we contract even harder. That pushes the baby's head even further. That causes even more stretching. Then the brain releases even more oxytocin. That causes even more stretching. And then the baby's head goes even further. And then that causes even more oxytocin. And then the uterus contracts even harder. And then the baby's head goes even further until finally, how does it all stop? Yeah, you squirt that little parasite out. You have to have a condition that will end the positive feedback loop. In this case, birth changes or terminates the loop. But notice, it wasn't negative, it was positive. We started with the uterus contracting and the cervix stretching, and as the loop went on, the uterus contracted even harder and the cervix stretched even more. That's a positive feedback loop, okay? Cycle is broken by the birth of the baby and a decrease in the stretch. There always has to be a condition that will stop the positive feedback loop. Other examples of positive feedback loops are lactation. So when the baby suckles on the nipple, that causes the ejection of milk. And the more the baby suckles, the more milk you eject. Blood clotting is another one. That's what we call the blood clotting cascade. Once it starts, a whole series of steps feed on each other to create even more. Now, we won't see those in Bio 201. Those are Bio 202. The one we will see later this semester is what's called an action potential in the nervous system. That's how a nerve impulse is generated. So we'll see that later. But for right now, make sure you know the difference between a negative and a positive feedback loop and that you know all the components. By the way, on the bottom left, we currently have that going on right now. The temperature of the planet is increasing, not by very much perhaps, but it's definitely increasing. What's happening is the permafrost is thawing up in the Arctic regions, and that's releasing carbon dioxide and methane, and that's trapping even more gas, and that raises the temperature even more, and so on. That's a positive feedback loop. And here we see a really bizarre picture trying to show the childbirth thing. You can work through that on your own. Got the woman trying to get that little parasite out of her body. So study that on your own. Goes with the example we looked at earlier. You have a homework assignment on homeostasis, and you're going to have a quiz on homeostasis, and as I mentioned before, you're going to get tested on homeostasis on your first exam. So you have both a homeostasis quiz and a homeostasis exam question coming up. That's how important homeostasis is. So what the homework and the quiz and the exam will all consist of, it's going to look just like this. You're going to get a scenario, an example, and then you figure out all the components, all right? So let's read this through together, and then you pause the video, figure it out on your own, and then we'll go over the answers together. So when your blood calcium level drops too low, the drop is detected by extracellular calcium receptor cells, which signal the parathyroid gland. The parathyroid gland then releases parathyroid hormone, PTH, which in turn promotes calcium reabsorption by the kidneys. Thus, less calcium is excreted in the urine, and the blood calcium level returns to normal. So I want you to identify the elements of the feedback loop, which one is which, what goes with what, tell me whether it's a positive or a negative feedback loop, and then tell me why it's either positive or negative. So pause the video, come back, and we'll go over the answers. Are you back? Did you figure it out? So the stimulus was the blood calcium dropping too low. That was the change that caused the homeostatic feedback loop to start into action. Who was able to tell that the calcium was too low? It was those extracellular calcium receptor cells, all right? They detected the change. They had to go a step further then and contact the hypothalamus, who is the control center. The hypothalamus is the one that's actually reading the blood calcium levels and saying either, yeah, these levels are okay, or no, these levels are not okay. The effector. This is where when I do it in class, I see a lot of mistakes. A lot of people put PTH as the effector. When you're trying to figure out the effector, you're trying to figure out who actually most directly causes the change to take place. It was the kidneys that were doing that absorption, okay? They were doing the calcium absorption. They are the effector. So how does PTH fit in? Remember, the two control systems of the human body, nervous and endocrine, whenever there's communication between receptor and control center, between control center and effector, that communication will usually take place using either a nerve impulse or a hormone. In this case, it was the hormone PTH that allowed the hypothalamus to talk to the kidneys. So PTH is just the text message, all right? It's not the actual effector. What happens as a result of this? The blood calcium increases. It started by dropping, now it's increasing. Therefore, that's a negative feedback loop. And how do you know it's negative? Because the direction of the original stimulus was reversed. We started with calcium levels going down, we ended with calcium levels going back up. Don't tell me that it's a negative feedback loop because it returned the body to normal. I'll mark that wrong, because that's not necessarily true. It can be the case that a feedback loop can't completely correct the problem. Your body's just not able to do that. That's when you have to go to the hospital. You have to get drugs or surgery or whatever. So it's not that your body necessarily returns to normal. It's that the direction of the stimulus is reversed. We started by going down. We ended by going up. If it were a positive feedback loop, it would enhance the original stimulus. It would exaggerate it. It would go more in the same direction. So make sure to tell me that when I ask why you said positive or negative. And yeah, this is Point Sublime at the Grand Canyon. I'll be here end of July or thereabouts. Thunderstorms at the Grand Canyon during the summer are just amazing. This was the middle of the afternoon. This is like 3 o'clock in the afternoon. These thunderstorms, the whole sky turns black on one side, and you watch the thunderstorm comes towards you, and the lightning sizzles and crackles and lights up the sky. The thunder shakes the ground. The storm comes on top of you. Torrents of rain come down, and 15 minutes later, it's all like it was. Kind of like homeostasis in nature, isn't it? I didn't even plan that. I swear I didn't. Oh my God, that's amazing. Okay, so this was the last of the annotated introductory PowerPoints. Next we'll start on the integumentary system.